Hi friends, happy Thursday. That is actually like a Friday. I hope that you are able to um, get outside tomorrow on Friday. It's supposed to be super nice, and then it's supposed to be kind of crummy weather this weekend. Um, so take advantage of that sunshine. It is good for you. It'll improve your mood and get you some vitamin D going and all those good things. So anyway, it's my little plug for outdoor adventures. Um, we are going to talk a little bit about the phenomena that you observed in the H2 Olympics. That was really introductory. And so now we're going to formalize some of the stuff that we observed and try to understand why it happened. So, before you move forward with these notes, I'd really like you to complete the Exploring the Water Molecule Part 2 activity. So you're just going to read two pages on Khan Academy. I think they're really well written, and the images are really, really good. So there's a little kind of guide worksheet that goes along with that, and it just has you take down some drawings and label some things, and I think it's going to help improve your understanding of how the polarity of the water molecule gives it these really unique properties. So once you've done that, you can go ahead and continue on with these notes. You can just put these in your notebook, write down the stuff in blue as usual, and here we go. All right, so one of the big things that the articles talked about is the intra, with an A, and inter, ER, molecular forces. I don't know what old dead white dude named these almost the same word, but I'm sure somehow it made sense in his brain, but it's really confusing for the rest of us, so thanks for that, dude. Intramolecular forces refer to bonds involving electrons. So polar covalent bonding is an intramolecular force. Ionic bonding is intra. Non-polar covalent bonding is intra because it's within the molecule. And then we have intermolecular forces, and those are between two different molecules. So in this case, we have an intermolecular force called hydrogen bonding, and it's super annoying to me that they named it bonding because it's not really a bond. Like in bonds, electrons are shared or transferred, but this doesn't involve electrons. Hydrogen bonding doesn't involve electrons. And so to me, that is kind of a confusing name, but again, I guess not anything we can really do about it right now. So the hydrogen bonding is just really these positive and negative ends of the molecule acting like little magnets. And so hydrogen bonding is special because there's such a big difference in electronegativity that this is a very polar bond. So the H is really positive and the O is really negative. So they form this really strong magnetic attraction, and it is hard to overcome. And that intermolecular force is really what makes water so special. The way that I remember these and keep them kind of like straight in my brain is that intramolecular is between atoms. So the A in intra stands for atoms. And so that's how I can remember it's like polar covalent bonding, or it's ionic bonding, is because it's between atoms. whereas intermolecular is between molecules. That's all I got. It's hard to remember. I would just really try to label a lot of water molecules with this and really like reinforce it in your brain. So now that we know about this hydrogen bonding intermolecular force that holds all of our little water molecules together, we can start to think about these unique properties. So one of these is cohesion. And cohesion means that water sticks to itself really easily. It's like really good at sticking to itself. And that's why water forms droplets on things all the time. So whether that's dew on grass or condensation on your car or condensation on your window in the wintertime, that cohesion, those hydrogen bonds pulling the water molecules together, are what allows that to happen. So when you were dropping pennies or whatever coin into that cup of water and it made that big bubble on the top, that big bubble of water that was like higher than the sides of the cup, cohesion allowed that to happen, because instead of just spilling over the side of the cup, the other water molecules held on to each other and prevented the water from spilling out. And in order for this to happen, water has to orient its molecules, so basically like arrange or move its molecules so that the positive and the negative charges are always beside each other. So you can see here red oxygen pointing towards white hydrogen, red oxygen, white hydrogen, white hydrogen, red oxygen, red oxygen, white hydrogen. And you could probably draw a little dash line there too, actually. And then this is more of that like 3D representation, just showing how they all get really close together and they're all attracting each other like tiny little magnets. So the next really important quality is adhesion. And adhesion says that water sticks to other stuff really easily. So because water has that positive and that negative side, if there is anything slightly positive or slightly negative around the water is going to stick to it. So put a positive sodium ion in there, and all of the negative oxygens get attracted to that cation, and they just like surround it. And this would actually be a sphere, but if we put in this whole sphere, we wouldn't be able to see the cation, so that would defeat the purpose, but it's like a cross section. And over here you can see that when we have an anion, all the positive hydrogen ends point towards that anion. And this, excuse me, so sleepy. This is what allows for water to sit on the surface of that penny so well, because it sticks to the penny, and then the cohesion allows for that big bubble to form on top. And so the penny really shows both the adhesion and cohesion. But water sticking to other things really easily is something that we observe all the time. Anytime we see a water droplet on something, we're witnessing adhesion because the droplet is stuck to something, and cohesion because it's many water droplets, or many water molecules stuck together. One of the most important qualities is a result of cohesion, and that's surface tension. So the ability of water's surface to resist an external force. And so if you look at a little water glider over here, right, you can see he's just making dents in top of the water. He's not breaking through the water surface, and that's why he doesn't sink. And surface tension happens because the molecules on top of the surface of the water are really strongly attracted to the molecules below them and the molecules beside them, but they're not very attracted to anything that's above them because it's just air. And air doesn't really have charged particles, and so the water isn't attracted to it because there's nothing for it to interact with magnetically. And so it creates this really strong layer of molecules. And so that allows our little water skippers to float on top. And if we think about the Water Olympics, the paper clips floating on top were indicative of surface tension, which is pretty cool. I actually, the first time I did that lab, I did not expect the paper clips to float. I was like, dang, water is really strong. All right, last piece here is talking about the soap and the little boat in the Water Olympics and why that boat was able to move. So to understand that, we have to kind of know what the molecule of soap looks like. So this is a soap molecule, and it has this really long oily tail, and this whole tail is non-polar. It's non-polar. The squiggles mean carbon, 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 and on each little point, there's two hydrogens. So two hydrogens, two hydrogens, two hydrogens, two hydrogens. And since it's all the same, it's not polar. Its head, though, is polar, has a double bonded oxygen. It's got an oxygen with a negative charge stuck to a cation, usually sodium. So this guy is charged and polar. So this part acts like a magnet, and this part does not act like a magnet. We know from experience or salad dressing that oil and water don't like to mix. They don't want to be together. And that's because these water molecules want to be with the other magnets, right? They're attracted to the other magnets, and so they all stick together, literally like stick. And then all of this oil is kind of left to its own devices, just like together, because all the water is attracted to the other waters. However, when you introduce this head group with a charge, it changes the game. So this head group now wants to interact with the polar water molecules. So when you put the soap in the water, there's this mad scramble for everybody to get next to something that's interesting to them. So all the water molecules are trying to get next to either other water molecules or the head group. They don't want to be next to this tail. The tail is like not important to them because it's just boring. It doesn't have any charge. So when you put the soap in the water, head groups want to come down like this, and they want to be with the positive and negatively charged water parts. So they want to be with the polar water molecule. All the tails end up getting left out here to their own devices. When this happens, it breaks the surface tension of the water, and all that motion and all that breaking of the surface tension is what causes the boat to move. So this is kind of above and beyond really what I need you to know. I just need you to know about cohesion, adhesion, and surface tension, but I did want to explain a little bit how this soapy water boat worked. All right, guys, that is it. I love you. Have a good weekend and get some sunshine while you can.